Hi, I'm Crispy. Welcome back to Making the mangoPi. Today we're going to be tying up the last loose ends before we get this board made. Let's get started. So the first thing I did off camera was I resolved almost all the DRC errors. Now, if we look at my DRC errors, I actually still have 27 of them, and they are all track width errors. So I've actually decided to keep all these DRC errors and not fix them because they're related to an issue I have with differential pairs. So if we zoom in where the camera connector differential pairs are, then I'll kind of show you what the error is. As I mentioned in a previous video, differential pairs need to have a very specific width and a very specific distance between them. Now this width and distance between them is dependent on whether you're on an internal layer or an external layer. So if we look at the mangoPi revision 2, we have the top layer and we have the bottom layer. And sandwiched in between those, we have 4 internal layers. Now with differential pairs, the widths of the traces and the spacing between them is dependent on if you're on an external layer or an internal layer. So the issue with the camera connector connections is that they start out on the top layer and then they go down to an internal layer. In this case, they go to the pink layer, which is inner 3. So basically what you have here is the internal layer section needs to have a specific width and a specific spacing, but then the top layer needs to have a different width and a different spacing. So that's why all these track width errors have come up, is because this has happened several other times. Like we have it with the PCIe here as well, where a signal is starting out on a top layer or the bottom layer, and then it's transitioning into a middle layer. So I think this is okay because this discontinuity with impedance is only at the very beginning and at the very end, and the majority of the signal is correct. That's why I've decided to ignore these, so I don't think it'll make a big difference, but we'll find out when we actually make the thing. So with the DRC errors done, let's actually move on to the bill of materials. So this is actually the third time I've had to create this bill of materials. The first time I took the pre-generated EasyEDA one and then made it into what I would need it to be, which is this much more in-depth bill of materials. But then the times after that have been, I would pick a component, put it on the bill of materials, and then just a few days later, it would go out of stock. There is a massive component shortage going on right now, which is why you can't get that graphics card that you want in your computer. Like everything is out of stock. I've had to change at least a third of the components on this thing. Now, most of the components that I needed to change were really simple passive components like resistors and capacitors. And those ones are fairly easy to change because you really just need to find a resistor from another manufacturer that's the same size, same resistance, and same tolerance values. And there's just a plethora of people that make resistors, so it's a pretty easy thing to change. The thing that scared me the most was that the Ethernet PHY chip, this one right here, this was out of stock, and this was not coming back in stock until the fall. And unlike a passive component, this is much more difficult to change if I needed to sub in a new component for it, because the footprints of it are more than likely going to be different. So I'd have to physically change this part of the PCB, and that's the best case scenario. From there, it can get even worse because integrated circuits are complex and their pinouts are not going to be the same, and they might even have slightly different functionality, or maybe a replacement Ethernet PHY chip needs to have an extra 3 GPIO signals. And you can just see how that turns into a ton of work. Now, luckily, I did find a really close cousin to this chip that I think the only difference is that the new chip is a little bit more expensive, but it has another feature added onto it. I'm not going to use the feature. I literally just got the chip because it was actually in stock, and actually bought 10 of them just so I have them on hand for future prototypes. So that crisis was avoided, and I think I only needed to change one of these pins. I made it into a no connect pin, which was a really easy change, and I'm just glad that that worked out. And that's basically it. It's just going through every component on your board and then finding what's in stock and what's out of stock, and then finding replacements for it. That's really all you can do. Next, let's move on to who's going to actually assemble this PCB. So I found this PCB assembler that's in Colorado called Advanced Assembly PCB, and so far I'm pretty happy with them. So I've talked to them quite a bit over email, asked them a lot of questions, and they've been very helpful and knowledgeable. And I really don't have any worries with them. They seem to do a good job. I mean, I've never done business with them before, but just initial impressions, it's been much better than working with the Chinese PCB assembler. So I think this is the one that we're going to go for. And finally, now that we've gone over the DRC errors, the bill of materials, as well as who's going to assemble the board, let's actually order the boards. So I've gone to JLC PCB, and if you click on Quote Now, it takes you to their PCB ordering page. First thing you should do is you should upload your Gerber file. You click on Add Gerber. Here's my Gerber file. Open. And this will take a second to load, so we'll do a jump cut. Now that the Gerber file is uploaded, we can select the other options we need to. First thing is layers. Uploading the Gerber file actually pulls the amount of layers from your board, so we don't need to click that, but it is 6. It also grabs the dimensions for your board. That's what you would enter here. PCB quantity, we're going to choose 5. Underneath that, we have different designs. So different designs means that you can have multiple designs on a board. So actually, if we look at this board here that I made, it has 3 different designs on it. This top half is an AC power controller, and then the bottom half, we split it in half. To the left here, we have a current limiting circuit, and then to the right is meant for an LCD screen that hooks up to an Arduino, and the Arduino is controlling this AC power controller. So you can have multiple designs on your board, and I think that this different design field is for if you want to have them make little scoring cuts in the final board, so it's easier to break them apart and get your separate boards out. I didn't do that on this board. I just take a hacksaw to it and cut through it. But that's what that is. So for the mangoPi, we don't need this option. We just keep it as one. Delivery format, once again, hobbyist. You can just do single PCB. These panels, I think, are for when you're doing like mass production of your board and you're like squeegeeing on solder paste to a bunch of to a bunch of PCBs at once, then you want those. But we'll get to that in a second. So single PCB there. PCB thickness, 1.6 millimeters is the standard thickness. Impedance, we do want impedance controlled because that's what all those differential pairs that we drew were, and we base them all around the calculation that we're using this stack up. Now a stack up is basically in your PCB you can have specific layer thicknesses and also use special materials that act as the dielectric, the thing that's making it so your layers don't short together in between layers. And by changing those around, you'll change your impedance requirements for your circuit. So we're just using their standard stack up because it'll be cheaper. Below that, we need to select in the Gerber files what Gerber files correspond to which layers. And now that we've selected all those, we can move on to the color. So you can choose whatever color you want here. However, if you choose something that's not green, then it does add to your cost and adds to the turnaround time. So I'm just going to use green for this board. If you have a simpler like 2-layer board, I don't think they actually charge you anything extra for the different colors, but you still add to the turnaround time. So it might just be better to go with green anyways. Underneath that, we have the surface finish. Now, the cheapest option is the Hassle with lead. Since the mangoPi has PCIe connectors, I'm actually going to be using this option because this is a gold-plated finish on top, and I think that will survive better with the wear and tear of a PCIe connector. Underneath that is copper weight. 1 ounce is pretty standard, and that's usually what I choose. If you do 2 ounces, it does add to the cost of it. And what this means is you're basically changing the thickness of the layers of copper on your board so you can handle more current with smaller traces. 1 ounce is fine for this project. Underneath that, we have the gold fingers. Now, the gold fingers are the actual PCIe edge of the board. In fact, if we go and look at the design and come up here, these would be the gold fingers on the board, this PCIe connection. So we want to click yes on that. And then the 45-degree chamfer, we want to click yes on as well. Underneath that, you have material type. The FR4 standard is standard, so we're just going to go with that one. You can confirm the production file, which is after I send them all the board files, they would create the production files that they need in order to make the board. And then they would send those production files to me to verify and give the go-ahead. And I honestly don't know what I would be looking for. And I don't know. So I'm just, no, I don't want to see them. I'm sure they're going to do it correctly. They know more than I do. Underneath that is a flying probe test. Flying probe test is actually pretty cool. They essentially have little metallic fingers that will touch every connection combination on your board and see if it is electrically connected or if it's not electrically connected, which is really helpful if, say, you have a via on your board that's a little bit too close to a trace and maybe it was drilled slightly off center and now suddenly this via is electrically connected to the trace. That would be very hard to debug on your own, but this flying probe test will actually be able to find that just by testing every single possible combination of connections on the board. So can't even deselect that. That's a great feature that JLC PCB just offers right out of the box. It's awesome. Castellated holes. I have no idea what these are for, and I know I don't need them, so no. And finally, for the basic options, we have remove order number. This does cost extra money, but I usually prefer just to specify the location. And if you want to, you can get a little bit tricky. So on the revision 2, this is going to be hard to see, but I actually have the order number placed right here, which corresponds with this giant integrated circuit. This is the SRAM, and the SRAM is completely hiding it. So you can still hide the order numbers that way, though it can also be nice to look at your order number because you can look at your order history on JLC PCB and go, oh hey, what Gerber files made this board that I'm looking at right now, and find it that way. So I usually just specify location. And now we're getting into the advanced options. So first one, I don't have vias that are less than 0.45 millimeters in diameter, so we can keep the standard option. The 4-wire Kelvin test is a more advanced test than the flying probe test, where I think they're just measuring electrical resistances of all your connections on the board to see if they're good connections or they're not connected, which we don't really need for this because it does add extra costs, so we're going to choose no on that. And finally, you can add paper in between your PCBs if you want to. I don't really care, so I can do that either. And that finishes up all the options for making this board. Underneath that, there is an SMT assembly option. Now this is a bit weird because you can only have JLC PCB assemble your board if all your components are on this website, LCSC Electronics. So this is their electronic supplier that's integrated with JLC PCB. And if all your components come from here, then they'll assemble your board for fairly cheap too. Unfortunately for the mangoPi with the FPGA and a lot of the more niche components, they don't have those, so the SMT assembly won't work for this board. But if you have a board that's just using LCSC components, then this could be a really good idea if you don't want to do the soldering yourself. Finally, underneath that, we have the stencil. So a stencil is basically just a thin sheet of metal that has cutouts on it that correspond to all the pads on your circuit board. In fact, let me just look for a images. And what this is used for is you lay that stencil on top of your board and then you line up the holes with all the pads on it, and then you take this stuff called solder paste, which is essentially a mixture of flux and little tiny solder balls, and you squeegee it onto the board, and then you remove the stencil, and now you have solder paste everywhere you need it. So you can place your components on the board and then use a hot air gun or an oven or whatever to melt all the solder paste and make it into solder. So for the mangoPi, we will actually be ordering a stencil because we'll be hand assembling a mangoPi revision 3 on the channel. So there are a few more options for the stencil. Framework, we're going to select no. I don't really know what framework means, but I don't think I need it, so no. Dimensions, the smallest dimension will work for our board because it's only a 100 millimeter by 100 millimeter, so we can just keep that as the default. We don't need a customized side. For stencil side, we're going to choose top plus bottom on the same stencil, and that just means that there will be cutouts for the top side of components and then cutouts for the bottom side of components on the same stencil. We only want one stencil, and then electropolishing, if you have really fine BGA components on your board, this is a good idea to do. I don't actually think I will for the mangoPi, even though we do have fine BGA components on the board, because it adds to the cost, and I'm probably not actually going to put solder paste on the BGA component area because it can cause bridging underneath it, which bridging is essentially when two solder balls that shouldn't be electrically connected are electrically connected because there was too much solder there and they melted and formed a little bridge in between each other. And that's not good because it's really hard to see, especially if it happens to a ball that's like in the middle of this BGA area. So I'm going to do no on that. Fiducials, don't even know if I'm saying that right. I don't know what these are. I think this might be for assembling, but we don't have any super fancy assembling machines, so we're going to leave that as a no. And that's everything with ordering your own PCB. So now I can just save cart and then continue with the checkout and get this board ordered. So off camera, I'm going to finalize that order for the PCB, talk to the PCB assembler, and start ordering components and kind of getting all these moving pieces together to actually make this thing a reality. So stay tuned for the next video where hopefully we will at least have the bare PCBs and maybe even an assembled PCB. Thank you so much for watching. I'll catch you in the next episode.